Today, we're going to be discussing a problem concerning entropy and Gibbs free energy. Let's take a look at the problem. When delta G naught equals 0, the system is at equilibrium, and both the forward and reverse reaction are proceeding at equal rates. This is the case during phase transition. Consider the phase transition in the data shown for BCl3 below. Calculate the boiling point for BCl3, represented by the reaction BCl3 liquid goes reversibly to BCl3 gaseous. Let's take a look at the information we're given. We know that we're considering a phase transition, which tells us that delta G naught equals 0, and we're given the heat of formation of both products and reactants, as well as the entropy S of both products and reactants. We now have to consider how the given information relates delta G, enthalpy H, and entropy S, while in the meantime trying to calculate boiling point T. Luckily for us, there's an equation that integrates all this information, also known as the Gibbs free energy, which is delta G equals delta H minus T delta S. We already know that delta G is going to be 0 because the problem told us we're in a phase transition, but we have to be a little bit careful. We're not directly given delta H and delta S. We're given the heat of formation of both products and reactants. But luckily for us, we can apply another formula in order to find both delta H and delta S. To find delta H, it's equal to the sum of moles of products times enthalpy of products minus the sum of moles of reactants times enthalpy of reactants. From here it's basically plug and chug. The last thing to consider, though, is the number of moles. We can tell from the reaction BCl3 liquid to BCl3 gaseous that it's a 1-to-1 molar ratio. So we take 1 mole of product times the enthalpy of the product, which is negative 395 kilojoules per mole, minus 1 mole of reactant minus negative 418 kilojoules per mole. Plugging into the calculator, you get 23 kilojoules, which, with a quick conversion, because you need like units, is 23 times 10 to the third joules. Now let's repeat the same thing to find our delta S, our change in entropy, which is the same formula, the sum of moles of product times entropy of products minus the sum of moles of reactants times entropy of reactants. Again, we see that there's a 1-to-1 molar ratio, so we have 1 mole of product times the entropy of product, which is 290 joules per mole times Kelvin, times 1 mole of reactant times 209 joules per mole times Kelvin entropy of reactant. This gives us a delta S change in entropy of 81 joules per Kelvin. Doing some quick algebra, we isolate T to equal delta G minus delta H over negative delta S. So let's not forget that our reaction is in phase transition, so that our delta G equals 0. So we have 0 minus our change in enthalpy, which we calculated to be 23 times 10 to the third joules. Note, make sure all your numbers are in the same units, and we divide that by negative delta S, which we calculated to be 81 joules per Kelvin. So we divide it by negative 81 joules per Kelvin. This gives us an answer of 284 Kelvin, but this wasn't applying a quick conversion, we subtract 273, which gives us a temperature of 11 degrees Celsius.